Okay, welcome everybody. It's my pleasure to introduce our next speaker. Today, Han Nguyen will talk about approximate Bayesian computation via the energy statistic. So, please.
All right. Thank you very much, Massey. And thank you very much for organizing, to all the organizers for organizing these sessions. I'm very humbling to be in the presence of so many esteemed academics and statisticians. And yeah, so I'm very excited to be giving this talk to you all. So yep, the talk today is going to be about approximate Bayesian computation via the energy statistic. And this is joint work that I've been doing with Julien Abel, Florence Forbes, and Hongliang Liu at the Statisfy team in INRIA in Grenoble. So if you see anything that's particularly wrong, or you have any particularly difficult questions, I'll ask you to forward those questions to them in the session, so they can definitely get back to you on that. So to outline the presentation, I'll firstly give a very brief introduction to approximate Bayesian computation. I don't think that is particularly necessary to go in depth, given the caliber of the participants in these sessions. And then I'll talk about the energy distance and its estimator, the energy statistic. Then I'll talk about how the energy statistic can be used in the ABC setting and some of its properties. And then finally, I'll show some numerical illustrations of the energy statistic ABC algorithm as we've applied it, and how it compares to other algorithms that are available. So to start off with, we let X be an IID sample of random replicates, Xi, where X lives in some real space. And X is random with a PDF that is parametric in form, with the form f of x given theta. And we'll assume that theta arises from some set T with the data generating process characterized by the PDF pi of theta. So conditional on theta, the likelihood of X is just the product, of course, of the likelihood of the individual observations. And then we can write out the posterior distributions PDF as being the prior multiplied by the likelihood weighted by the Bayesian constant C. So in the ABC setting, we usually suppose that for some reason or another, the likelihood f of x is infeasible to compute, but it's feasible to simulate a sample of size m from the likelihood of x. So we let y of m be a sample of size m from the same likelihood as that of x. So the likelihood of y is just the product of each of the individual likelihoods, since it's an IID sample. And we suppose that we can also sample from our prior. So let k be simulated from the PDF pi theta. And then with that prior that we've simulated, we simulate our data y of size m of k from the PDF conditional on that sampled parameter value theta k. And together, those two, ymk and theta k, forms a pair, zmk, which we'll put into the set Zn, And so the goal of a simulation-based inference scheme is to use this set Zn to somehow approximate the posterior distribution pi of theta given x. So to construct such an approximation, we'll use the notion of a discrepancy function. So we let d be a discrepancy function in the sense that d is greater or equal to 0, and it measures the difference somehow between x and y, where x and y are two samples. And we let w be a weight function. So here the weight just has to be greater or equal to 0, and it's decreasing in d, which is always positive or always non-negative, and it's calibrated by some parameter epsilon, which is greater than 0. Using the weight and the discrepancy function, what we'll do is we'll approximate the likelihood of f of x by the distance of y with respect to the discrepancy weighted by the function w. So we'll take the integral of the weight of the discrepancy between x and y calibrated by epsilon on average with respect to y. So in the language of Zhang et al. 2018 in AI Stat, we call the pseudo-posterior PDF approximation pi m of epsilon as being the posterior constructed from the prior multiplied by this approximate likelihood function and then normalized. So the ABC algorithm that is characterized by the scheme from the previous slide is then given as follows. What we do is we input some observed data, xn, some discrepancy function d, and some weight function w, calibration parameter epsilon, and sample size m of simulation samples that we want to construct. Then for every k between 1 and big N, we simulate a prior value. We simulate data that's conditional on the prior. We compute the discrepancy between that data and our original sample, x. And then we put the discrepancy in the set D, and we put the data and our parameter set that we've sampled into the set Z. And then using Z and D, we'll approximate the posterior distribution using the following discrete measure. So all we do is we take the weighted discrete measure with respect to the sample of size n. So here, for example, if you take the weight function to be the identity function, not the identity function, the indicator function that d is less than or equal to epsilon, then you just get back the ABC procedure for the usual rejection ABC. Okay, so how does the energy statistic fit into all of this? Or what is the energy statistic to start off with? And then how does the energy statistic fit into all of this? So first of all, to define the energy statistic, we need to define a function delta, which is said to be symmetric of negative type in the sense of Sejtinovic et al. In the Annals of Statistics 2013. So basically, it's a function, I think it's basically a function, a metric without the triangle inequality that is a negative definite function. And then what we do is we take independently x and x prime from the probability measure pi of x, and then y and y prime from the probability measure pi of y. And then we define the energy statistic or the energy distance based on this semi-metric of negative type delta as being e delta to the power of a half, where e delta is this distance between the probability measure of x and the probability measure of y, which is 2 times the expectation of delta of xy minus expectation delta x, and its clone x prime minus expectation of delta y and its clone. So it turns out that these energy distance definitions have nice properties. So for example, under the quite mild condition that the expectation of delta and its of delta of x and its clone is finite, and of y is also finite, we have the condition that the energy distance must always be greater or equal to 0 and equal to 0 if and only if the two probability measures are equal within the space where this moment condition is satisfied. Okay, so given delta specifies the energy distance, an infinite number of possible choices of delta. I guess one problem is to choose a delta that is particularly or has particularly good properties. So the original paper that introduced the notion of the energy distance, Kelly and Rizzo, 2004, studied the particular case where you take the delta function to just be the L2 norm, the Euclidean distance between x and y. So we denote the particular case where we use this energy distance. We denote the particular case where we use this delta as being just E without any subscripts. Okay, so we let phi of x and phi of y be the characteristic functions of the measures pi of x and pi of y respectively. Then under the condition that the expected norm of x plus the expected norm of y is finite, we know that the energy distance has the closed form that is proportional to this function, the two characteristic functions. So we note that this function is actually just a weighted L2 norm, or a square of a weighted L2 norm between the characteristic functions. And upon noticing that, we can make the observation that e to the power of a half here must be a metric over the space of probability measures with finite first moments. So where e of x plus e of y is less than infinity. Okay, so that's a pretty useful property to have, and that's something that we'll come back to in the future. Okay, so given that we have this notion of a distance between probability measures, that still doesn't help us because we often observe these probability measures through samples. So we have to estimate this distance from the samples. So suppose that we observe samples xn and ym from the measures pi x and pi y. Then we can estimate the energy distance between the two measures using this particular statistic, which we'll call the energy statistic. So we see that this V statistic consists of terms that you got 2 times this term here that computes the delta between x's and y's, and then you subtract this term here that has the delta between x's and themselves and between x's and between y's and themselves. This forms a V statistic, which means that it basically has the same properties as a U statistic other than the unbiasedness property. So for brevity, if V of delta is the energy distance for any particular delta, then we take V without deltas being that of the Euclidean norm. And it turns out that like E being a metric, that V to the power, the root of V is actually a metric over the set of finite discrete measures. So this sample version also inherits the metric properties of the limiting version. Okay, so finally, we say that if we apply the ABC algorithm using the discrepancy being the squared, or using V, or the square of the energy statistic metric, then we call that the energy statistic ABC algorithm. Okay, so in the previous works of Park et al. 2016 and Zhang et al. 2018, both in AI stats, and and others in 2019 in JRSS B, the authors considered the maximum mean discrepancy for use in the ABC algorithm. So it turns out that if you look at the maximum mean discrepancy, the statistic that estimates the maximum mean discrepancy has this form here, which is basically just a sign swap of the form for the energy statistic, except you replace these semi-metrics with Mercer kernels instead. So it turns out in a paper by Stojtinovic et al. In Annals, referred to previously, that these Mercer kernels that generate these MMD functions, these MMD estimates, actually have a generative relationship with semi-metrics of negative type. So if you have a particular Mercer kernel, you can always generate back a semi-metric of negative type and vice versa. And so basically any kind of property that the energy statistic ABC algorithm has at large basically also applies to any MMD based ABC algorithm as well. Okay, so we'll start off with presenting the most general result that we derived that applies to our algorithm and other algorithms as well. So if we suppose that x and y are samples with PDFs, f of x given theta naught and f of y given theta, respectively, and assume that the discrepancies converge towards some limiting discrepancy that is a function of theta naught and theta that characterizes the data generating processes of x and y, almost surely as n and m goes to infinity. And if we take w, the weight, to be a piecewise continuous and bounded function, that w is continuous, particularly at this point of convergent, then we have this pointwise limiting convergent property regarding the ABC pseudo posterior PDF. So the ABC pseudo-posterior PDF, that should be an N over there, will, well, I guess it doesn't matter because M and N between free. So basically, what this says is that the ABC pseudo-posterior will converge to a posterior distribution that is basically a weighted region of the discrepancy function between the two set of parameters that characterize the data generating processes of X and Y, weighted by the prior distribution and then normalized. So can everyone still hear me? I've switched off my video, so hopefully everything is better.
Yeah, I think now it's a bit clearer than before. Thanks.
Okay, great. Thanks, Michael. Okay, so this result is just a simple generalization of Zhang et al.'s result in their 2018 paper, where they've only proved the result for the case of the rejection ABC. So that's the case where you take the weight as being the distance less than epsilon. So in the particular case of the energy statistic, that is the Euclidean distance energy statistic, a sufficient condition to verify this almost sure convergence of the discrepancy to some limiting value is for your two random variables to both have second moments, in the sense that the expectation of the squared L2 norm of both variables are finite. And if that is true, then of course you have the fact from the previous result that your discrepancy will approach some limit that is a function of your characteristic functions of the data generating processes that generate X and Y. So that's a handy little result to have. So let's visualize what this looks like. So suppose that we have some parameter theta, the conjugate normal case. So theta is normal, would mean 0, variance tau squared. And we observe a sample xn, IID, from a normal distribution with the mean being 2 and variance sigma squared. Then the analytic solution for the posterior is, of course, your usual conjugate relationship. So if we note that we can analytically analyze this in closed form, because we know that the distance between theta naught and theta as x and y goes to infinity, or the n and m go to infinity, in the energy statistic case is just the square of the distance between them. We can consider what the energy statistic ABC pseudo-posteriors look like for certain values of the epsilon calibration cutoffs. If we consider the algorithm based on sampling Y from the same data generating process as X. So Julian made these really nice plots. So this is the case where we use the weights as being the usual rejection weight. So the more blue the lines are, the greater the value of epsilon. So epsilon is smaller for the red lines. And the black curve there is your prior distribution. So we see this truncation of the prior distribution, this truncation, and then this weighting by the prior distribution going on here. It's quite obvious. And in the case, quite popular case, where people take the weight to be a Gaussian weight, we get these concentration shapes, which are smoother to work with. So we see that the more blue they are, the greater the value of epsilon. The red, more red, the smaller the value of epsilon. So the tighter the variance is around the point theta naught. Okay, so that's an asymptotic result regarding n and m going to infinity, which may not always be practical. So a more practical result is a finite sample result, considering when epsilon goes to 0. So here we have the simple result that if n and m are the same, and we just take the rejection ABC algorithm, and the likelihoods are continuous and interchangeable, and we have basically just two boundedness conditions. So global essential boundedness condition and a local essential boundedness condition. Then in the L1 norm, the pseudo-posterior PDF of the ABC algorithms will converge to the true posterior PDF as epsilon goes to 0. So this is just a direct application of a theorem from Burnton and others in 2019, and using the property that the energy distance forms a metric space over the set of finite probability measures. As a comment, I guess, Burnton and others also provided results regarding the situation when epsilon and n go to the respective limits at some rates simultaneously, and largely our setup inherits the properties because it largely inherits them through verification of the assumptions that they've set out. So there are those properties as well, but not particularly interesting in my particular view, just because of the extra assumptions regarding the rates. Okay, so let's consider some numerical study of our ABC algorithm. So for our numerical study, we'll stick to the basics. We'll stick to the case where we use the rejection ABC using the energy distance or energy statistic as our discrepancy measure. We'll take a sample of 10 to the 5 replicates for our simulation. Take m is equal to n in each case. Always take epsilon post hoc. I said quantile twice, but yeah, so take epsilon post hoc to be a 5% quantile of your discrepancy function. And we'll check out how the energy statistic works compared to some previously considered algorithms in the same class. So for example, we'll have a look at the MMD maximum mean discrepancy using the Gaussian kernel, which is usually the only kernel that gets used in the literature. And that was, I think, to the best of my knowledge, first considered by Park and others. The Kurak-Leibler discrepancy, which was considered in Zhang and others, and the swapping distance version of the Wasserstein discrepancy that was considered in Burnton and others. Okay, so for our first set of results, we look at a classic, just a Gaussian mixture case. So we take a realization X, which is 500 observations from a two-component Gaussian distribution with component weights 0.3 and 0.7, and then opposing means. So the mean of the first class is 0.7, 0.7. The mean of the second class is negative 0.7, negative 0.7, and these two covariance matrices. And our goal is, of course, to approximate the posterior distribution of the parameters given this random sample. So to do so, we'll sample from a prior distribution where we sample our mixing proportion uniformly between 0 and 1, and we'll sample our mean vectors between -1 and 1 uniformly as well. And then use the same process as the generative process otherwise. So in this particular case, we see that for the top row here, we have the estimates of mu naught, so the two coordinates of mu naught. For the bottom row, we have the two coordinates for mu1. We notice that KL and the Wasserstein tend to have what appears to be smaller variance than our and MMD in mu naught, but the energy statistic and MMD seems to have smaller variance in terms of mu1. So it's hard to say if any of them are particularly better than one another. So for our second study, we'll generate 200 replicates of observations arising from a moving average process, two lag moving average process. So each observation is a time series of length 10, and the moving average is driven by student T noise with 5 degrees of freedom, and the two moving average parameters are 0.6 for the first lag and 0.2 for the second lag. To construct our ABC sample, we'll sample the first lag from uniformly from -2 to 2, and the second lag uniformly from -1 to 1. And of course, we'll generate the data in the same way as for X. We'll generate the simulated data in the same way as for X, except replacing theta star, the generative parameters, with our simulated parameters. So in this particular case, again, theta naught on the x-axis, theta 1 on the x-axis, theta 2 on the y-axis. We see that there is not too much difference, again, with respect to the outcome of the 4 assessed algorithms. Okay, so finally, we'll look at a bivariate beta distribution case, simulate 500 observations from a bivariate beta distribution where x1 is dependent on these parameters and x2 dependent on parameters 2, 4, 3, and 5. So they each miss one of the 5 parameters that they're dependent on. To fit this, we simulate the parameters uniformly in the 0 to 5 hypercube. And we simulate y simply by using 5 independent gamma random variables. So this is a particular case where the likelihood is more complex than the data generating process for simulation, as were the previous. Okay, so in this particular case, the 4 different colors indicate the 4 different algorithms that have been assessed. And again, these 4 algorithms are pretty much effectively giving you the same kind of outcomes on this problem as well. So we should probably ask the question as to whether or not any of these algorithms actually have anything over the other ones, and we may consider that question from the computational complexity point of view. So it turns out in the univariate case that all of the algorithms are basically sorting based algorithms, and so they all have n log n complexity order. But in the multivariate case, interestingly, the Kupak-Leibler method retains the n log n complexity, whereas the energy statistic and MMD, because they basically do the same calculations, and the swapping distance approximation of the Wasserstein have order n squared complexity. If you wanted to use the exact Wasserstein instead of the swapping order, the swapping distance Wasserstein, that would cost you an extra load of computation due to having to run the linear programming algorithm. So that becomes an n to the 5 on 2 log n order algorithm, which is probably far too slow for practical use. So when we checked empirically whether or not these timings checked out, they did seem to check out. So in the Gaussian mixture case, for varying n, we see that the energy statistic, MMD, and Wasserstein are basically parallel at a point, whereas Kupak-Leibler grows at a slower rate. And again, we observe that in the moving average case, which really prompts the question as to why aren't we making the final conclusion that the Kupak-Leibler method should be preferred over the other methods that we assessed. Okay, so why not Kupak-Leibler? So Zhang proposed the use of this particular estimator for the Kupak-Leibler divergence. So this estimator is nice in the fact that it basically just comes down to sort operations, and it converges almost surely to the Kupak-Leibler divergence between the probability measures pi x and pi y, but it's not applicable in discrete cases. And we can observe that because this denominator min of j not equal to I of xi minus xj here will be equal to 0 with non-zero probability if you use a discrete distribution. So this is really only practical in the continuous case, and as a practical note, only in a continuous case where your data are of a given precision level. Because if you observe data that have been rounded or have been quantized, then again, you go back to a discrete case and this becomes not applicable again. So yes, this is going to be faster and provide you with relatively the same level of performance as the other algorithms, but it does have this caveat of not being applicable in certain cases. Okay, so lastly, I want to finish off by asking the question whether or not we can justify using the energy statistic or MMD over the other methods. And one way that one might consider justifying the energy statistic is to propose an estimator that retains some good properties that has faster time than the other methods. So one such estimator is this one here. So what we can observe is that because the energy distance or the energy statistic is a V statistic, it has this expanded form where kappa delta here is this kernel that is a function of the semi-metrics. So Gretton made the observation that you can unbiasedly and consistently estimate the energy distance based on delta using a sample average where you kind of just skip every second sample. So you put every sample into a list because they're independent. You can kind of just skip every second sample and you can evaluate this expression, and you can take a sample average, and that sample average is of course just a linear complexity operation. And what you lose is, because you're skipping every second observation, basically you are working with effectively half of your data. But if you only care about asymptotics, then maybe that's not so important. So of course, this being an unbiased estimator has the particular risk that it can be less than zero with non-zero probability. So of course, we can always make this a biased but consistent estimator by taking the max between 0 and it. And that would give you something that meets the general convergence property, our first theoretical result, that has effectively order n complexity. So that's a potential future direction that we might take with this research. So that's all I really wanted to say. So here are the references which you can inspect when the slides are uploaded. So thank you very much. That's our current archive article. It's a bit dated now, doesn't incorporate some of the results that we've established since then. But we'll be uploading a new one soon. So thank you very much for your attention.
Okay, Jen, many thanks indeed for the very interesting talk. Some virtual claps from my side. And we now open the floor to questions. So please use the raise the hand icon to announce that you have questions, please.
Hey, Matthias.
Hi, Ben. How are you?
Yeah, good. How are you doing?
Great talk. Can you hear me?
Yeah, I can hear you.
Yeah, not too bad.
Oh, now I
wondering,
can't.
yeah, in one of the examples, or in at least a couple of those yeah, let me see. Can you hear me now?
I can hear you now. Yeah.
Yeah, I think there's a massive lag, but let me ask my question. So in some of those examples, you could compute posterior distribution using Markov chain Monte Carlo, say, and compare that to your ABC posteriors. Have you tried to do that to see the discrepancy between the actual posterior and your ABC posteriors?
No, we haven't, and perhaps we should, mainly we haven't due to time constraints, really, and the unwillingness to write the MCMC algorithms. But yeah, no, that's an excellent point. It would definitely provide an extra dimension of clarity and reveal whether or not any of the particular algorithms are even correct.
Yeah, thank you so much.
No, thank you for your question.
Any further questions? Perhaps while we are waiting, I'm raising my hand with a question. So you discussed the connection to MMD, and if I understand correctly, there's like a one-to-one correspondence to certain kernels.
Yes.
So I was wondering, what does then your perspective bring in, like, added value to the table? Does it open up some new perspective in terms of theory, or does it allow for some indeed computational shortcuts that the MMD perspective wouldn't provide?
I think that that's an excellent question, by the way. I think that it comes down to this relationship down here, that our method, because we know what the limit of the energy distance should be, of the discrepancy function should be, and the limit is characterized by the characteristic functions. If somehow you have a nice form for this characteristic function squared distance, then that would provide you with effectively a closed form solution for your limit. So I think that that's one additional perspective that the energy statistic gives in this particular case. Of course, the MMD provides other benefits because in certain cases you can bound unbounded processes in using MMDs, because you can use a Gaussian kernel, for example, which is bounded, whereas the squared distance is not going to be bounded. So MMD might be applicable if you're looking for certain properties as well. So I think depending on what you're after in terms of your final conclusion, you pick a kernel or you pick a semi-metric that suits that particular outcome.
Okay, many thanks. So in the numerical simulations, so in the results there, so you mentioned for MMD you use the usual Gaussian kernel,
Yeah.
but since the results are a little bit different to what you obtain with the energy statistics, so what kind of kernel would the energy statistic correspond to?
I am unsure. Yeah, no, I'd have to get back to you on that. But the reference of Sejtinovic et al. They provide the functional relationships between the kernels and the semi-metrics. There's also the property that certain semi-metrics. You said before one-to-one, but it's not quite one-to-one. These semi-metrics map to certain reproducible kernel Hilbert spaces, and back vice versa. So they map to equivalence class of kernels, basically.
Okay, thanks. Other questions?
Yes, Dennis?
Hi, thank you. So this is a general question. I don't entirely know if it makes sense. Thank you very much for your interesting talk, by the way. So in a kind of classic ABC setting where you use summary statistics, you're very much picking which features of the data you're particularly interested in. With a energy distance setting, through your choice of underlying metric, you're kind of implicitly focusing on some features of the data. Is there what's a good way of choosing this metric and kind of deciding on the features you're particularly interested in? I hope that's a sensible question.
Yeah, no, I think that that's a very sensible question and deserves much more attention than I've been willing to give it, which is 0 currently, because that's quite complex. This Stinovic paper, unpacking it, is, I think, a good, will probably yield the solution to that, because it presents a set of relationships between the potential semi-metrics and what kind of kernel Hilbert spaces they map into. And of course, you want to map into a kernel Hilbert space that has some particular geometries that you want to preserve within the class of distributions that you want to compare. So that's a potential way of being able to choose, is to start off with a particular kernel with a nice kernel Hilbert space that you care about, and then to work backwards, or to just use that kernel in the MMD setting. It's quite equivalent using the energy statistic or the MMD setting.
Okay, thank you.
Thank you for your question.
Any further questions? If not, I think we thank our speaker again for the very interesting talk. And then we'll see you again in 2 weeks' time when Chris Rovandi will be giving a presentation. Thank you very much, everyone.
Thank you, organizers.